All right, guys. So in the last video, Praveen ended up talking about some of the voltage and current sources that you're going to encounter in in Engineering 17. All of these 6 devices, the independent voltage source, independent current source, and then all 4 of the dependent sources are ideal basic circuit elements. There's one last ideal basic circuit element that I want to talk about. I'm sure that most of you guys have heard about it. It's what they call a resistor. So this section is on electrical resistance and a very famous law called Ohm's law. Now, one of the properties of a resistor that's extremely important, and it's something that we're going to have the opportunity to prove later, is that a resistor is always a passive element. Now, by this we mean something very specific. We mean that this element always consumes or dissipates electrical power, and it never generates it. So unlike sources, voltage sources and current sources that sometimes, depending on how they're placed in the circuit, sometimes they can generate electrical power, like batteries usually do, and sometimes they can consume them. Resistors will always, under all circumstances, consume electrical power. So here, it always, or it consumes. Another way to say consumes is dissipates electrical power and never generates it. Now, suppose you had an ideal basic circuit element. It's represented by this black box. It has 2 terminals. And suppose that I place a voltage across its terminals, and this element draws a current like this. One of the quantities that we can construct is the ratio of the voltage across the terminals divided by the current that flows through it. This, by definition, is the resistance of this element at this particular voltage and this particular current. Now, if it so happens that the voltage and current, as you change the voltage across this element, if it happens that it's always the same value, the same quantity, then the element inside of the box is what we call a resistor. So for a resistor, this ratio R of the voltage to the current is constant for all values of the voltage V and current I. Now, the schematic symbol that we have for this element has 2 terminals, and it looks like this, and it is characterized by its resistance value R. Now, very briefly, let me talk a little bit about the resistance. It does have some units, and the units of resistance can be obtained by the definition over here. This is a volt per ampere, or amp. This also goes by another common name. This is what we call an ohm. And we usually use the Greek letter omega, capital omega, to denote the resistance. Now, if it's true that the resistance for this particular element is constant for all values of the voltage and the current, notice that this equation that defines for you the resistance can actually be rearranged by multiplying both sides by the current. So if I take this definition and multiply both sides by I can actually rewrite it like this. This is the result mathematically that I wanted to get to. This is what's called Ohm's law. Now, notice that Ohm's law itself can also be expressed as an IV characteristic curve. So if we happen to have a set of axes here, where along the vertical axis we have the current and along the horizontal axis we have the voltage, then this equation itself can actually be rewritten and rearranged such that I is equal to 1 over R times V. This is in the form y equals mx plus b, where the correspondences are such that I is equal to y, v is equal to x, and the slope here is equal to 1 over r. So if this happens to be constant, then the IV curve for resistance is going to look something like this, or the slope on this IV graph is equal to 1 over r. One extremely important property of resistance is that resistance is always positive. There is no such thing in nature as something that has negative resistance. One last thing that I want to make mention of is that we can also apply the passive sign convention to Ohm's law. And to do this, we can actually talk about two separate cases. Suppose that in each case we have a resistor characterized by a resistance like this. For the first case, we define our voltage to have this polarity, and suppose that the current is going down this way, while for the second case, we have the voltage with the same polarity across each one of the terminals. However, we have defined the current to go in the opposite direction. Since Ohm's law, V equals IR, is a relationship that relates the voltage to the current, the passive sign convention actually applies. And remember, whenever the current is in the direction of the voltage drop, any relationship that relates to the voltage to the current takes on a positive sign. And if the current is in the direction of a voltage rise, then any relationship that relates to the voltage to the current takes on a negative sign. These are things that we need to build in by hand. So over here, notice that this current is going from the positive terminal through the resistor down to the negative. This current is going in the direction of the voltage drop. So Ohm's law is written as V equals IR. However, in this case, the current is going from the negative terminal up through the resistor to the positive. This is going in the direction of the voltage rise. So we must build into Ohm's law by hand this minus sign. So if your teachers in high school told you that Ohm's law is always V equals IR, they only told you half the story. Is V equals plus or minus IR depending on the direction of the current in relation to the voltage. Thank you for watching, and we'll cover more about these things in the next following videos.